Um, hello, guys. Just one reminder about the example classes. The example classes are on Tuesdays and Thursdays. Tuesdays, two of them on Tuesday and 2 of them on Thursdays. It's important that you do come to the example classes, right? It's important that you do come, and because that's the only time, well, that's part of the time that you can spend trying to do the problems by yourself, right? And in mathematics, as you know, you learn things by doing problems, right? You learn mathematics by doing problems in your time, right? So therefore, it is important that you do come to the example classes. All right, today I'm going to continue with this one here. This is page 8 of the lecture notes. So starting with the exponential distribution. The exponential distribution is one of the simplest distributions in statistics. The density function of the exponential takes this form, right? And lambda is known as the rate parameter, and lambda always takes values strictly positive. So it always takes strictly positive values. If you draw a graph of the f of x versus x, it will look something like this. Okay. Some properties of the these are some properties of the exponential distribution: the expected value, the variance, and the MGF. For the MGF will exist only if lambda is greater than t, right? And the notation, this is the notation I shall use to denote an exponential random variable, right? So exp in brackets lambda is the parameter, okay? Right. So that's exponential. The next one, so that's number 5. Number 5 is the gamma distribution, right? For this, the notation I shall use is the following. GA for gamma. It has two parameters, R and lambda. Okay. The density function is, sorry, I meant A and lambda, not R, A and lambda. All right. And the density is defined on the positive real line that x is strictly positive. Okay. And the parameters A is known as the shape parameter, and it takes values strictly positive, and lambda is known as the scale parameter. It also takes values strictly positive, right? And this function here, I asked this in the tutorial, just from the one I had from 3 to 4. You guys said that you did not know this function. This is known as the gamma function. So, and is defined to be the integral from 0 to infinity of, so this is the definition. This is the definition of a gamma function. Okay, and I must say one thing, that you should not confuse the gamma function is a mathematical function, right? Whereas this one here, what I have written here is the gamma density function. These two have nothing to do with each other. This is a gamma density function, and this is a gamma function. I mean, this is a mathematical concept, whereas this one here is a statistical distribution. They have nothing to, I mean, you should, I know, I've seen over the years I've been teaching this course, a lot of people confuse this with this. They are two separate things, right? This is a mathematical function, whereas this one is a density of a statistical distribution, right? This is used, the gamma function is used to define the statistical distribution. They are not related to each other, right? Okay? All right, anyway, now let me give you, I mean, since many of you said that you don't know what this is, so let me tell you, just give a few properties of the gamma function, right? The first property is that gamma at a plus 1 is a times gamma of a. That's a property, well-known property. Gamma at n is n minus 1 factorial if n is oh, sorry. Right? That's the second property. If n is a positive integer, then gamma of n is n minus 1 factorial. So gamma at half is root of pi. And the last property, which is the most important, gamma of A is this is the most important property. I think a lot of books, I've seen several books, papers, and where they get this property wrong, because, I mean, the correct version, what I have written down here is the correct version, right? The gamma function is defined everywhere on the rail line, except at the point 0, -1, -2, etc. All right? I mean, in some books I have seen, they said that the gamma function is only defined on the positive rail line, which is not true, right? The gamma function is defined in both positive and negative rail lines, but excluding these points, right? So at these points, at the point 0, -1, -2, etc., the gamma function does not exist. In other words, gamma at 0 is infinity, and gamma at -1 is infinity, and so on, right? Okay. Okay. So these are some properties of the gamma function. Now, let's return to the gamma distribution, which is what I wanted to talk about, not the gamma function. The gamma distribution has the following properties. So the first property is the expectation of x is equal to A divided by lambda. So here I'm talking about the gamma distribution, not the gamma function, okay? The variance of x is equal to A by lambda squared, and the MGF of x. Now, I told you last week that I think this was question 6 in sheet 1. I would show you how to derive it, but I didn't have time. So let me show you how to do it now. Okay, so this is the definition of an MGF. So okay. Now I'm going to make the following substitution. I'm going to make okay. So if you make the substitution and sub this into this, you will get this, right? Yes? Right. Now, yes? Now, this guy here, if you look at the definition, this is the definition of the gamma function, right? So this is the gamma function. This must be equal to the gamma function at A, okay? Because of this, right? And therefore, what you have is lambda by lambda minus t forward to A. So this is the MGF of a gamma random variable, okay? All right, guys. So the next one, so this is number 5, number 6. Number 6 is the Gumbel distribution. Oh, sorry, not Gumbel, sorry. Beta, I missed one. It's the beta distribution. I'm sorry, guys. It's the beta distribution. And the notation I shall use for this one is this. And the PDF This is the PDF of the beta distribution. I will explain in a minute what B is. Just give me a sec, okay? Before I do that, let me talk about the range. The x in this case is limited between 0 and 1. That is the unit interval. And A1 and A2 are both known as shape parameters. Okay, parameters, sorry, plural, okay. Now, the function B is known as the beta function, right? This is known as the beta function. Just like the gamma function, this is also a mathematical function. Once again, this function is a mathematical concept. It has nothing to do with the density function here. The density function here is the density of a beta distribution. It's a statistical concept, whereas this is a mathematical concept, right? And it's defined as is A1, okay. This is the definition of a beta function, right? It can also be defined as follows. Right, so both these two definitions are equivalent to each other, right? They are the same, right? Whereas this one here, once again, this is the PDF of beta this is the PDF of the beta distribution, not so once again I must emphasize, not enough times, that this is a statistical concept. This defines the beta distribution, which is a statistical concept, whereas these two are the definitions of a beta function, which is a mathematical concept, right? So you shouldn't confuse these, right? They are two separate things. Right. Now, the expected value of a beta variable or beta random variable is this, and the variance of a beta random variable is this, all right? Okay, so, and once again, you may ask me, what is the MGF? The MGF is it does exist, but it's complicated. It's really, it involves some special function. You really don't want to know what it is, because you wouldn't see that in the rest of your lifetime. So don't worry. So it's really complicated function. Okay. The next one. So the number 6, number 7 is Gumbel. This is the notation for a Gumbel random variable. The PDF of a Gumbel is the Gumbel variable is defined from minus to plus infinity, the whole real line. Yeah. And the mu parameter is also defined from minus to plus infinity. The sigma parameter is strictly positive. The mu parameter is known as the location parameter. And sigma parameter is known as the scale. Sorry, it's a scale. Okay, guys. Now, some properties, the expected value is given by this number here, mu plus and also the CDF. Can you see this, guys? The CDF is given by this equation. Now, let me ask you guys, I ask this question every year, but nobody has been able to tell me the correct answer. Now, these numbers here, this number here, and this number here, where do you think they come from? I know you guys have done a lot more mathematics than I am. I mean, probably. Have you seen those numbers before in your math courses you have taken? No? Yes, no? You haven't seen these numbers before? And you don't want to try? This number, 0.57722, is known as the Euler's constant. Euler is a mathematician. I'm sure you probably heard of his name. He's a Swiss mathematician. He made a lot of contributions to mathematics and also other areas. So, whereas this number here is simply pi squared divided by 6. So if you square pi, you get this number, right? Okay. If you want to see how they come about, if you want to see how these numbers come about, try integrating this density, and you see. Try integrating this density. You will see how they come about. Okay. Okay. Right, now, one thing I haven't mentioned for this distribution is the moment generating function, right? The MGF is okay. Now, this is the definition of MGF, right? This is the PDF. So I have multiplied the PDF by E of Tx, and I want to integrate from minus infinity to plus infinity. Now, obviously, we need a substitution. In this case, I'm going to make the following. I'm going to make the following substitution. So x is equal to mu and dx by dy is minus sigma over y, right? So you should make this substitution into this, yeah, into the integrand. You will get the following. You get E of Tx will become E of and then okay. Now the limits of integration. When x is minus infinity, y will be plus infinity, and when x is plus infinity, y will be 0. So the limits go from plus infinity to 0. You see that a lot of things now cancel. If I have a right pen with, yeah, here we are. This guy goes with this guy, this goes with this, and I'm going to use the minus sign to switch the limits around. So this will be 0 to infinity of okay, and this will be E T mu. Now, you can write this guy here as, what would this be equal to, guys? This is equal to y now, let me ask you, I just showed you a few minutes ago, I talked about this function. I talked about this integral a few minutes ago. What is that? This integral here is equal to? Come on, guys. I just talked about this. What's this? This is a gamma function at 1 minus t sigma. You already forgotten or what? I just talked about it a couple of minutes ago. Here we are. This one. This is the definition of the gamma function. So using this definition, you can write this as this, right? Okay. All right. Okay. All right. So what we have shown is that the MGF we have shown that the MGF of a Gumbel random variable is equal to this, right? Yes? Okay. So so you should, I mean, if I ask you things like this, you should be able to do things like this. If I ask you, say, in the test or the exam, it's not really difficult to do. Okay? All right. Now, this next one. So that's number, which number is that? It's 7. So the next one is number 8. Fréchet is a French mathematician, not as well known as Poisson, but the notation I will use for this is right. This is the notation. This is the notation for a Fréchet random variable with parameters lambda and sigma. The PDF is defined this is the density function of the Fréchet distribution, and is defined on the positive real line. There are two parameters, lambda and sigma. Both take positive values. Lambda is known as the shape parameter, and sigma is known as the scale. Okay. Right. There are some properties. The first property is the CDF. The CDF corresponding to this can be written like this. Okay, the expected value can be written like this, provided lambda is greater than 1. Okay? And the variance can be written like this, where lambda is strictly greater than 2. Now finally, the MGF does not exist if t is greater than 0. Now, if you look at the problem sheet for this week, that is sheet number 1, the questions there are all about showing how an MGF does not exist. So if you haven't tried those questions, right? If you haven't tried those questions, you can start with this one, right? Try to show that this one, that the MGF for this does not exist, right? Now let me show you, just to help you guys when you go to the example class. I know today in the example class from 3 to 4, I needed to give some hint about how to do these things. So let me help you, right, how to show, for example, in this case, all right, let me help you how to show that this one, for this distribution, the MGF does not exist, all right? So that's what I'm going to do now. For this one, let me give you some hint, all right? Let's take consider the case that lambda equal to 1 and sigma equal to 1, right? In this case, the f of x is equal to 1 divided by x squared, okay? This is the density function, right? And we want to show, we want to show that the MGF does not exist. For this distribution, we want to show that the MGF does not exist if t is greater than 0, all right? So the trick is as follows. So what you do is you start with the definition, which is, this is the definition of an MGF, right? And in this case, it will be yes? Yeah? Now, the idea is to show that the MGF does not exist, you need to show that this integral here is equal to plus infinity. Remember what I said last week, guys. If you want to show that something does not exist, then you must show that that something is equal to plus infinity, right? So in this case, to show that this doesn't exist, you need to show that this integral is equal to plus infinity, right? Okay? Right, now to do that, I'm going to use the following trick, right? The trick is as follows. E of tx This is the famous Taylor series expansion. I'm sure you know this, guys. Yeah? You've seen this before, right? This is the Taylor series expansion for the exponential term. Now, since we are assuming that t is positive and x is also positive because you're integrating from 0 to infinity, what you're doing here is you're summing an infinite sum of positive numbers. Therefore, what you have here is that e of tx is a sum of infinite sequence of positive numbers. Therefore, it must be greater than any single term of the infinite sequence, right? For all k. You understand what I'm saying? Because what you have here, guys, is an infinite sum of terms, and each term is a positive number, right? And therefore, this must be greater than this for every k. Yeah? Now, I'm going to use this. I'm going to use this inequality to show that this integral is equal to infinity. Now, the trick here is to choose the value for k. K is any number from 0, 1, 2, up to infinity. Is to choose the value for k so that this integral becomes equal to infinity, right? So, I mean, in your case, since you don't have the experience, you need to do it by trial and error. But in my case, I know, given my experience, I know what value to choose for k so that this integral becomes bounded below by something equal to infinity, right? So I'm going to choose k to be equal to 1. If I choose k to be 1, then this guy here will be greater than okay. Okay. Are you guys with me? I have chosen my k to be equal to 1. So that using this inequality, we can say that this is greater than tx. And this is equal to this. Now I'm going to make a further substitution, y equal to 1 over x. So x equal to 1 over y. So dx by dy is minus 1 over y squared. So under this substitution, right, you get t from infinity to 0 of y e of minus y minus 1 over y squared dy. Okay? And the minus sign here, I'm going to use that to switch the limits. So this will be t 0 to infinity, 1 over y, e of minus y, dy. Now, once again, guys, do you recognize this integral? This integral is equal to, just a minute ago, what is this integral equal to, guys? Talk to me, guys. Huh? Gamma at what? Gamma at, what's the argument here? Huh? 0, right? It's 0. And as I said, gamma at 0 is undefined, doesn't exist, right? So this is equal to plus infinity. So what we have shown, guys, is that we have shown that this MGF, going back here, we have shown that the MGF is greater than plus infinity, but nothing can be greater than infinity. Therefore, the MGF must be equal to plus infinity, meaning that MGF does not exist. Is that clear, guys? I mean, this is when you go to the example class from 5 to 6. I'm not done with the class yet. When you go to the example class from 5 to 6, this is the trick you're going to apply. Okay? Is to find the value for k. I mean, since you are just beginning, you may need to try different values for k, right? But anyway, is to find the value for k so that the lower bound, in this case, the lower bound is this one, is equal to plus infinity. So if you can show that the lower bound is equal to plus infinity, then you will have shown that the MGF is equal to infinity, and therefore it doesn't exist. Okay? Right. Okay. I hope you understand what I mean. All right, so this is the Fresher distribution. The next one, number 9. Sorry. Number 9. I've got a couple of minutes to go. Number 9 is the Weibull distribution. Weibull is the name of an engineer. It's the name of it's the name of a Swedish engineer. He worked for the famous car, the Swedish car. I'm sure all of you, if you guys know all about cars, you would know what I mean. The famous Swedish car company. So he worked for that company long time ago. The notation I will use is this is the notation. The PDF is given by this is the PDF of the Weibull distribution. There are two parameters, lambda and sigma, both positive. This is known as the shape parameter. And this is known as the scale parameter. Some properties. The first property is the CDF is this is the PDF. The CDF is given by this formula. The expected value is given by this, and the variance is given by this. The MGF you'll be surprised to know that the MGF of the Weibull distribution was derived only in 2015, as early as a couple of years ago. You should know who this person is, right? You can, you know what I'm saying. Yeah, if somebody called this name, you should know who that is. Sorry. All right. So this is that's it for today, guys. So when you come, we got an example class. We got an example class from 5 to 6, right? So if you belong to that group, please could you come to G205 in Alan Turing.
In the last example, why I think we can choose k to be 0 and it'll be easier.
No.
No?
No.
Because if you choose k to be 0, here any k is fine. So you can choose k to be 0 and this one is 1. Yeah.
Yeah. But
And
if this is 1, then
then you can see this comes
yeah,
with
but
1.
yeah, but then the
Then you can find this is the antiderivative of this to be e to the minus x to 1 over x.
yeah.
Because
But
its derivative
no,
is
no,
this
no,
one.
no, because this is antiderivative of this, but then the integral of this will be equal to 1, not infinity.
Not infinity?
Not infinity, no.
No?
No.
Because
Just try it. It will not be equal to infinity. You need to choose k to be 1.
because you let me see.
Yeah, try, man.
Okay.
You have to choose it to be k equal to 1.
All right.
Yeah.
All right.
You're
Thank
right, sir. You okay? Okay, same question. Okay.